Hello, Riles. For lesson 5.4, we are going to start looking at some special angles and special triangles for which we can get exact values of trig ratios without a calculator. First, let's review how we can use sketches to help us solve equations. This equation is kind of different in that we're not just asked to solve for principal angles. We're going to be asked to solve from -1 rotation to 1 full rotation. Here's my advice. We haven't had a lot of practice where our ratio is a decimal. So in the past, we've been using our definition first. And I see the sine ratio, so I'm going to define the sine ratio to be the ratio of y to r. But yeah, the thing about ratios, that's a y, is that ratios can be represented as fractions. But ratios can also be represented as percents. So, well, I could say, all right, we're going to draw a circle of radius 1. Here comes the sketch part, definition first, then the sketch. Yeah, draw a circle of radius 1 and y value of 0.707. You can also just think of this as your y value is going to be about 70% of the way up your radius, like that. And sketching that is going to show me where my two principal solutions are, theta 1 and theta 2. But then the other solutions, and I guess I'll just break my convention about the numbering system, is going to be back here, theta 3, and back there, theta 4. So I'm expecting 4 answers between -360 degrees and 360 degrees. In my sketch, I can see that my calculator is going to give me theta 1. Still, I think I might just introduce the beta symbol. Beta is going to be the inverse sine of 0.707. There's something special about this number here that we might not recognize yet. Am I in degree mode? Yeah. And sine inverse of 0.707. And I get to the nearest degree, 45 degrees. And 45 degrees is kind of a special angle because it makes a slope of 1. It's half of 90 degrees. And now I'm set to find theta 1. Theta 1 is 45 degrees. I guess that's an approximation. Okay, theta 2 is going to be the second quadrant angle with a related acute angle of 45 degrees. Let's try 180 degrees minus 45 degrees. I want to get used to this angle here, 135 degrees. It's going to show up a lot. For theta 3 and theta 4, I'm not so sure that I'm going to sort of see it on my sketch. I mean, I could say, oh, it's back 45 degrees from -360 degrees. I think I might just use the idea of coterminal angles instead and say that theta 3, which one did I label it? I guess theta 4, doesn't matter how I order them, is going to be 45 degrees minus 360 degrees, back 1 full rotation to get my other solutions. And theta 3 is going to be theta 2, 135 degrees minus 360 degrees. This gives me -315 degrees, and this gives me -225 degrees. I think I should double check those. I'm usually not this fast with subtraction, but again, these angles are special. They show up a lot, so I'm familiar with at least the absolute values. Okay. So yeah, to discover the relationship of the special angle and the special ratio here, let's go back to a SOHCAHTOA build. We can do this in standard position if you want by drawing a right isosceles triangle in standard position. I'll do that in a sec. I'll show you a different way of generating it. But in this diagram, it says we have a right isosceles triangle. Okay, it's an isosceles triangle, but it's also a right triangle. Being a right angle triangle means I have an angle of 90 degrees in there, but I still know in an isosceles triangle, these two angles are going to be the same measure. And that means that the sum of these two angles with 90 degrees, 2 thetas plus 90 degrees, has to equal 180 degrees. That means that the sum of those two angles together has to be 90 degrees, which means that individually each angle is going to be 45 degrees. Okay. So this is referred to as a 90 degree, 45 degree, 45 degree right angle triangle. And every right isosceles triangle is going to have angles of 90 degrees, 45 degrees, and 45 degrees. Okay. If I wanted to find trig ratios on 45 degrees, then for sine ratios and cosine ratios, I would need to know the length of my hypotenuse, or my r value. Let's just keep things exact here. Let's solve for the exact length of the hypotenuse. I'm going to say r squared is going to be 1 squared plus 1 squared. Be very careful with 1 squared. It's very easy to do, but it's easy to get wrong. 1 squared means 1 times 1. A square, that is 1 centimeter by 1 centimeter, will have an area of 1 square centimeter, not 2. This means that r squared is going to equal 2. And then normally we would be reaching for a calculator, but we don't need a calculator here. We want the exact value of the radius, the square root of 2. This number has some important historical context. There were cultures that didn't believe in irrational numbers. They thought that every number could be written as a ratio. They had a hard time figuring out, if I built a square that was 1 centimeter by 1 centimeter, what the length of the diagonal would be. They thought that maybe if they built squares large enough that they'd be able to measure that hypotenuse exactly, and it was impossible. They didn't understand that there was such a thing as an irrational number. Okay. So yeah, this triangle then, the 90 degree, 45 degree, 45 degree triangle, is also sometimes called a 1, 1 root 2 triangle. Now, the reason why I'm going to do another development for you here is to convince you that this length does not need to be 1. If I have an angle of 45 degrees in standard position, then I know that this line is going to have the equation y equals x. And that means that whatever x is, y will be the same thing. So I'm going through a comma a. Okay, you could call it 1a if you like, but now we don't need to say, well, what if this isn't 1? It's definitely 1 something. Maybe it's 1/3. Maybe it's 1 square root of 7. It doesn't matter. I don't need to memorize the value of r as long as I know the equation of the circle. It's just going to be the positive square root of the sum of the squares of the coordinates here. That's going to give me a square root of 2a squared. Now think back to in Unit 1 when we simplified radicals. I'm allowed to take the square root of 2 separate from the square root of a squared. And that means that my radius is going to be the square root of 2 times larger than this right here. And I like this construction better because it means that I don't need to memorize that this is 1 centimeter. It means that if this were 7 centimeters, that would be 7 centimeters, and that would be 7 times the square root of 2 centimeters. Okay? It's a special triangle, right isosceles triangle, AA root 2a, if you like. Now, let's write the primary trig ratios for angle A, I suppose. Notice that my opposite is going to be the same as my adjacent. And then here's my hypotenuse. Or if we want to use XYR definitions, angle A is 45 degrees. And in 45 degrees, here's my X, here's my Y, here's my R. That means that the sine of 45 degrees, which is the ratio of Y to R, is going to be A to root 2a. Or in this triangle, it would have been 1 centimeter to the square root of 2 centimeters. Whether I'm dividing out centimeters or a's, I get the ratio 1 over root 2. The exact value for that ratio. And I don't need a calculator to do that. In fact, I should be able to explain and illustrate why that's the case. Now, this number is irrational, and it has an irrational number. It is sometimes the denominator, let's say, is sometimes rationalized. So we sometimes write times root 2 over root 2, and say we could write this as the square root of 2 times 2. I generally don't ask you to rationalize your denominator. Calculators that will give you exact values will often spit out a rationalized denominator. I don't think there's any problem leaving your answer like this. The other two primary trig ratios, the cosine of 45 degrees is going to be the ratio of x to r. Well, notice that my x value is the same as my r value. That's also going to give me 1 over root 2. 45 degrees is special because your adjacent and your opposite are going to be the same. Your x-coordinate and your y-coordinate are going to be the same along the line y equals x. The tangent of 45 degrees is even easier, though. In fact, if you look at the tangent definition, that the tangent of theta is the ratio of y over x, it might look a little bit like rise over run. The tangent of theta actually measures the slope of your line if you're in standard position. And in standard position, my ratio of rise to run, my ratio of y to x, is a to a. And as long as a isn't 0, that's going to be 1. This is why I don't need a calculator to figure out that the tangent of 45 degrees is 1. And I can start to understand what this trig ratio is actually measuring. Okay. You don't need to memorize these ratios. You don't even need to memorize this triangle. You should understand that if you're at an angle of 45 degrees, you're going along the line y equals x. And we'll use it to find exact values in other quadrants as well. Okay. Does not matter what the lengths are. What we're looking for is the ratio. This is what is called a special triangle, as it allows us to calculate exact values for some trig ratios without the use of the calculator. Okay, for other angles, I'm going to do a different construction than this one here. Let's start with 60 degrees. The things that's special about 60 degrees is that 60 degrees shows up inside an equilateral triangle. Is the interior angle of an equilateral triangle. That means that all these side lengths are the same length. Okay. Now, if I want to use XYR definitions or SOHCAHTOA, notice that this triangle has been cut in half. And when I cut it in half, that bisects this side length. The base is bisected. Because the base is bisected, I'm not going to make my original side length of the triangle be an integer like 1. That would be difficult to cut in half. I'm going to make it 2. I'm going to make it 2a. Again, to show you that it doesn't matter how long we make it. 2 times something. Okay. So we say if my radius is 2a, because it's bisected, that means that my x value is going to be 1a. And then I can calculate my y value. My y value is going to be, oh, here, I'll show you. R squared is going to be x squared plus y squared. That means that 2a squared is going to be a squared plus y squared. 2a squared is going to be 2a all squared is going to be 4a squared. It's 2 times 2 times a times a. There's an a squared plus a y squared. Subtract 1a squared from both sides really carefully. You don't take off the a squared. You take away one of those a squareds. And you'll get 3a squared equals y squared. In this case, I know that my y value is positive because I'm in the first quadrant. So I get y is the square root of 3a squared can be simplified to the square root of 3 times the square root of a squared, which is just a. So instead of memorizing a 1 root 3 2 triangle, I like thinking of it as an a root 3a 2a triangle. And because this line right here bisects the side length, it also bisects the angle, which means this angle left over is 30 degrees. I'll likely show you this triangle drawn in standard position elsewhere. Okay, so I could try to memorize this triangle, but it might be better to visualize constructing it as having had been an equilateral triangle originally that was of side length 2a. We split it in half. That means that you have one 60-degree angle and one 30-degree angle. And notice what we can do in here. Let's look at, say, the sine of 30 degrees, the cosine of 30 degrees, the tangent of 30 degrees, and then the sine of 60 degrees, the cosine of 60 degrees, and the tangent of 60 degrees. The sine of 30 degrees is going to be the ratio of, if I turn it sideways so that it's in standard position, it'd be the ratio of y to r. We can use SOHCAHTOA if we're inside a triangle here, so I'll just use the ratio of the opposite of the hypotenuse. It's a to 2a, which is always going to be exactly 1/2. The cosine of 30 degrees, the ratio of the adjacent to the hypotenuse, is going to be root 3a over 2a. And I don't want to round off root 3. I want to keep it exact. I haven't needed a calculator yet. That's always going to be the square root of 3 divided by 2. And the tangent of 30 degrees, the ratio of the opposite to the adjacent, is going to be a to root 3a. I'll usually leave it as 1 over root 3, but you could rationalize it to root 3 over 3. I like this one better. Okay. 3 more values, 3 more trig ratios that I shouldn't need a calculator to be able to determine. For the other angle, I just sort of exchange my opposite and my adjacent. And we're going to notice something interesting here. We're actually going to understand what the co in cosine means in a sec. Sine of 60 degrees is the ratio of the opposite to the hypotenuse. That's going to be root 3 over 2, and that sounds familiar. The cosine of 60 degrees is going to be the ratio of the adjacent to the hypotenuse, or x to r. A to 2a is going to be 1 to 2, and that sounds familiar. And the tangent of 60 degrees is going to be the ratio of the opposite to the adjacent. Less familiar, but still seen those symbols before. So here's what I want to point out. Notice that, first off, that 30 degrees and 60 degrees, those are 2 angles that add up to 90 degrees. They're called complements, or complementary angles. Okay. Complementary angles. Remember supplementary angles, complementary angles, PLTZ, all that stuff from grade 7 and 8 and 9. So yeah, notice that the complementary sine, the cosine, the complementary sine of 60 degrees is equal to the sine of the complement of 60 degrees. And notice that the complementary sine of 30 degrees is equal to the sine of the complement of 30 degrees. This is why it's a bad idea to read this as sin, cos, and tan. Okay, when you say cosine, you are closer to understanding that you are taking a sine ratio of the complement of an angle. Okay. Using these triangles and your own sketches and definitions, you can find exact values for any angle that have related acute angles of 30 degrees, 60 degrees, and 45 degrees. Let's try it out. Find the exact value for the following. A calculator is not required. Let's sketch and explain. Sketch and explain. I'm probably just going to do this orally because the spacing is a little bit tight here. So, 135 degrees. Let's start with the angle, start with the sketch. 135 degrees I recognize as being somewhere between 90 degrees and 180 degrees. If I grab my calculator and do 180 degrees minus 135 degrees, oh, I recognize that angle. This means that we have a related acute angle of 45 degrees. Now, I don't think you need to draw a triangle here, and I don't think you need to use the cast rule either. If we say that we have a related acute angle of 45 degrees, that means that we're along the line. Our terminal arm is the line, y equals negative x. That means I know I'm going through the point negative. I could be heading towards the point negative 1, 1, and I'll do that this time. No, I always want to use ratios. I'm going to go back a, up a. Okay. So I'm going to say if x is negative a, that means that y is going to be positive a. And to get the cosine ratio, I'm going to need my r value. My r value is going to be the positive root of the sum of the squares of x and y. That's going to be the square root of a squared plus a squared, which is the square root of 2a squared, which is the square root of 2 times a. Before my sketch, I could have used my definition that the cosine of theta is the ratio of x to r. So I need to know what x is, and I need to know what r is. Or I don't need to know what x is. I don't know what x is. I don't know that it's -1. I know that it's negative. But if it is negative something, my r value will be the square root of 2 times that thing. That's what's really important here, is that we're not measuring lengths. We're measuring the ratio. So we're ready to conclude that the cosine of 135 degrees is going to be the ratio of the x value. If x is -a, then my r value is root 2a. And there I've shown, without memorizing and without touching my calculator, that the cosine of 135 degrees is exactly -1 over root 2. Okay. Let's try the next one. Tangent of 240 degrees. Let's start with the definition this time. Tangent ratio is the ratio of x to y, or y to x, sorry. Then I sketch the angle 240 degrees. 240 degrees, you might start to recognize it's past 180 degrees. It's not as far as 270 degrees. You don't want to say that it's 30 degrees off of 270 degrees. You want to say that it's 60 degrees off of 180 degrees. Okay, we have a related acute angle of, I should be showing that work, 180 degrees minus 45 degrees is 45 degrees here. 240 degrees minus 180 degrees is 60 degrees. Okay. And I've seen 60 degrees in an equilateral triangle before. Equilateral. So if I decide that I want my radius to be 2a, that means that this side would have been bisected. So x is going to be, notice I know that x has to be negative. I don't need to memorize that the tangent ratio is going to be positive in this quadrant. I know that my x value is going to be negative. And it's going to be -a because it's bisected. In this question, I need to know my y value. You say, oh, I can't remember what that y value was. Do I need to look up at my triangle up above? Do I need a formula sheet? No, the formula that I need to know is the equation of the circle, or the Pythagorean theorem. You might want to try a rearranged version, though. I'm going to say y is going to be the opposite of the square root of r squared minus x squared. I've seen students use the Pythagorean theorem in a rearranged way when they're solving for a leg instead. What I like doing here is setting the fact that y has to be negative because we're down here in quadrant 3. My y values are negative down there. This is going to tell me that my y value is going to be -2a all squared minus -a squared. So y is going to be negative. That's going to be 4a squared minus a squared. Notice the negative squaring becomes positive, but that negative remains negative. Y is going to be negative the square root of 3a squared. So y is negative the square root of 3 times a. And that means that the tangent of 240 degrees, which is the ratio of y to x, is going to be, now watch this, negative root 3a over negative a. Those two negatives eliminate and give me a positive ratio. Those two a's eliminate and give me the ratio root 3. Of course, the tangent ratio is going to be positive here, but make sure you show your reader the two negatives dividing out. Otherwise, I'm going to assume you've just memorized the cast rule and you don't understand why the tangent ratio has to be positive there. Okay. One more. Negative 570 degrees. Well, this we're looking for the ratio of y to r. Negative 570 degrees. Well, that's definitely smaller than or further than negative 360 degrees. Let's figure out how much. Negative 570 degrees plus 360 degrees is boop, 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 negative 210 degrees. I might be equipped to handle this right now because I recognize that negative 210 degrees, probably by inspection, has a related acute angle of 30 degrees. Maybe that should be a little bit lower. Okay, if not, then I could do negative 210 degrees plus 360 degrees is boop, 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 150 degrees. And then my related acute angle is 180 degrees minus 150 degrees, which is 30 degrees. Now, 30 degrees is half of the angle in an equilateral triangle. So my construction is going to be very similar to part A here. I'm going to swing up here so that I have space. If I make my radius 2a, then notice in this case it's my y value. That is going to be 1a, and I see that on my diagram. And I notice in this case my y value is going to be positive. It's positive because I see it on my sketch. And it's half of that because it's been bisected. For this ratio, this one's going to be a little bit faster because look, I don't need to calculate that x is going to be negative root 3a. All I needed was the ratio of y to r. I know r, I know y. I'm good to go. The sine of negative 570 degrees, notice, is going to be the same as the sine of negative 210 degrees because 210 degrees, negative 210 degrees is coterminal to negative 570 degrees. It is related to the sine of 30 degrees because 30 degrees is negative 570 degrees is related acute angle. So all of those definitions that we learned in 5.1 and 5.2 become useful here. The ratio of y to r is going to be a to 2a, which will always reduce down to 1/2. Okay. Try to imagine each one of these questions as a communication question. I know if you build your triangle once, then you can just use it to find all the other values, but you're likely going to be asked to do this without a calculator, and the easiest way to make sure that a student understands what's happening without a calculator is to ask them to explain it. So try it out.